Hi, this is a brief tutorial on syntax and parsing. If you need to write code to parse an expression, this is the video for you. I'm just going to give you a basic introduction to parsing. It's a complex subject, but I'm going to tell you all you need to know to get started. In particular, I'm going to talk about top-down parsing, and I'm going to describe recursive descent parsing, which is the simplest algorithm and the only one you'll really ever need. So in this video, I'm going to start by talking about the format of the input. That is, I'll cover the ideas of grammar and syntax notation. I'll also talk about the output from the parsing algorithm. That is, how will we represent the result? Then I will describe the recursive descent parsing algorithm. And if you're parsing expressions, I'll also talk about how to evaluate the resulting expression. And finally, I'll close with some commentary. So our goal is to write code that will parse an arithmetic expression. Here's an example of the input we'd like to be able to handle. We see that it's got identifiers like x, it's got numbers, it's got infix operators that take two operands, it's got prefix operators like the negation, and we see parentheses. In addition, an expression may also have postfixed operators, and factorial is the example of that. And it may have other things like function calls and so on, but these I'm not going to discuss. Before we go any further, I want to mention precedence and associativity. Remember that some operators have greater precedence. So for example, this expression here should be interpreted this way and not this way. If the user of your parser intends to have this interpretation, then they had better add parentheses to the input to the parser. With associativity, remember that with certain operators of equal precedence, like subtraction and addition, we want to process them in order. So this expression, for example, would be interpreted this way and not this way, which would give a different result. So our parser will need to take into account the proper precedence and associativity of the expression and its operators. Before we can code up our parser, we need to describe exactly which expressions are to be accepted. That is, we need to describe the language of expressions that our parser will accept. And to do that, we're going to provide a grammar for expressions. A grammar defines a language, and here I have a simple grammar for expressions. And let's go through it and take a look and see what we have. In every grammar, we'll see a number of rules. Okay, so here we see rules for E, rules for T, and rules for F. These things, E, T, and F, are called non-terminal symbols or grammar symbols. And this is the syntax for expressions. So these rules define exactly what it means to be a legal expression. We also see in these rules, on the right-hand side, both non-terminal symbols like E, T, and F, as well as terminal symbols, basically everything else. So we see plus, minus, the asterisk for multiplication, slash for divide. We see ID, integer, and some parentheses. These are called the terminal symbols, and they are not defined in the syntax for this particular grammar. Some of these, such as plus and minus, are literal things. Okay, they are just single characters. Others, like identifier and integer, stand for classes of inputs. So there are many different identifiers, many different integers. There are some variations on grammar notation, and I wanted to mention one important one. So here's our original grammar, and we're showing the same exact grammar down here. We have three rules for E, but we're collapsing them using a vertical bar to indicate OR. So an E, that is an expression, is either a term plus an expression, or a term minus an expression, or a term. By the way, E stands for expression, T stands for term, and F stands for factor. So if you multiply a bunch of factors together, you get a term. You add a bunch of terms together, you get an expression. For our purposes, we're going to define identifier as one or more characters. So this notation here means one character followed by 0 or more. characters. The braces mean 0 or more. We'll define integers as 1 or more digits. So again, you have the curly braces. Another notation you might see is curly braces with a plus sign, and that means 1 or more occurrences. So these two are equivalent. Many programming languages have slightly more complex definitions for identifiers. For example, we might define identifiers as a single character followed by 0 or more characters, digits, or underscore characters. A programming language might also define tokens like floating point numbers and so on, but we won't go into that here. When we scan one particular identifier, that will be a token. So our input consists of a series of tokens. The token could be an identifier, it could be a plus symbol or a multiplication symbol or a parenthesis, an integer, and so on and so forth. So we'll view the input as a sequence of tokens. Before we can parse the input, we need to break it up into a sequence of tokens. This is known as the lexical analysis part of your parser. And we have a lexer, sometimes called a tokenizer, that performs this tokenization of the input. So it'll read the input and break it into tokens. So in our organization, we will assume that we have a function called scan token. I'm not going to specify it here, but we'll assume that it scans the input, reads in from the input, and we've got a variable called next token. And every time we call scan token, it will set this variable to point to the newly scanned token. I'm going to assume that we're using an object-oriented programming language, and so we'll represent tokens with objects. So here's an object of class integer, and here's an object of class identifier. I show my objects this way, and the class integer has a single field value, and the class identifier has a single field called string, which points to the actual characters that are involved in the identifier. The goal of our parser is to read in some expression, such as this one right here, and produce some output, so some representation of the expression. So the first representation of this expression is shown right here, and this is the simplest. You can see that we add x and 5 first, and then negate that, and then we multiply that with 2. So this tree here reflects the meaning of this expression. We'll represent the tree with objects in a pretty much straightforward one-to-one way. We'll have classes called multiply, negate, add, subtract, and so on, as well as classes for identifier and integer. So this tree right here is naturally represented with this collection of objects. Let me be a little bit more precise about how we're going to represent expressions. We're going to use these classes here. So we've got a class called add, subtract, multiply, divide, negate, identifier, and integer. We'll also have a class called tree node, and all these others will be subclasses of that superclass. So these are all different kinds of tree nodes. So for the infix operators like add and multiply, we'll have two fields in the class called left and right, and these will contain pointers to other tree nodes. Depending on what kind of sub-expressions are being added together, well, that will determine what exactly is down here being pointed to. For prefix operators, like negate, we'll have just a single field called arg, or argument, and that will point to some tree node. You're probably going to want to have some way to print out an expression. If for no other reason, you'd like to verify that your parser is working correctly by printing out the internal representation that the parser is producing. So let's suggest that we have a print method for each one of our classes. These are going to be recursive methods that call each other. So for example, the class multiply, or any other infix operator, would work like this. It's got a pointer to the left subtree and a pointer to the right subtree. What print is going to do when called on this particular node is print an opening parenthesis, Then it's going to call itself recursively to print out whatever is pointed to by the left pointer, then an asterisk, then call itself again recursively to print out whatever is pointed to by the right field, and finally a closing parenthesis. A unary operator, like the negate class, just has a single field pointing to its argument, and it will print an opening parenthesis followed by the negate symbol, followed by the subtree, whatever it is, and then a closing parenthesis. So for example, if you have this particular expression, okay, it's going to print out something like this. You'll see it's got a lot of parentheses, but that makes sure that the output is exactly unambiguous, so you can be sure exactly what your representation is. I should mention that if for some reason you get a cycle in your tree and you try to print this out, you run into an infinite loop. Okay, you just keep printing 5 times 7 plus and so on. Let's assume that your parser has read in an expression and built an internal representation of that expression. Now you'd like to evaluate the expression. So for that, what we'll do is have an eval method implemented in each of the various classes that we have. So, for example, in the add class, we've got an eval method that simply calls itself recursively on the left subtree, then calls itself recursively on the right subtree, adds them together, and returns the result. So each one of these eval methods is going to evaluate the subtrees and then return the final value of that complete expression. A unary operator, like negate, would simply call itself recursively on the subtree, negate that, and return the resulting value. If the node happens to be an integer, then the eval method simply returns its value. If the node is an identifier, then, well, we have to figure out what the current value of that variable is and return it. We're now ready to describe the top-down recursive descent parsing algorithm. We're going to have a bunch of functions, one for each non-terminal grammar symbol. Each of these functions will scan a bunch of tokens and will return a pointer to the tree that it builds to represent whatever it parsed. So for example, parse will parse an expression and return a pointer to the tree for that expression. Parse will parse a term, and parse will parse a factor. At any moment, we'll have a variable called next token, which will contain the next unscanned token from the input, so we can look at it and see what's coming up. We'll call our lexer function scan token to advance to the next token, that is to read in some more input and see what the next token in the input stream is. If there are any problems, and by problem I mean the input is not grammatically correct, then these functions will return null. So here's the overall organization of the program. We'll have a couple of variables. Next token is a global variable that's shared among all the parsing functions, and we have a variable called result tree. So what our program is going to do is start by scanning the first token and then calling parse to parse the entire expression. That builds a representation, which it returns, and we store that in result tree. Then we might print out that tree to see what it is we read in, or we might call eval to evaluate the expression and then print the result. After we parse the expression, we need to make sure that the next thing on the input is the new line or the end of file or the end of input. Otherwise it's an error, because we could have some kind of input like this. Here we can scan an expression properly, no problem there, but we need to make sure that the next thing is not anything else besides the end marker. Let's look at the function that parses a factor, which can be an identifier, an integer, or an expression inside parentheses, or a negation symbol followed by another factor. So the function is basically just an if statement. We check the next token to see whether it's an identifier, an integer, an opening parenthesis, or a negation sign. If it's an identifier or an integer, then we simply return the token itself. More precisely, we return the object that represents the identifier or the integer. If the next token is an opening parenthesis, then we scan past that opening parenthesis to the next symbol, and then we call parse to parse an expression. Call it A. We can check to see whether there was an error, and if so, we just return null. And then we make sure that the thing following the expression is a closing parenthesis, and we pick that up, and finally we return the expression. If it wasn't a closing parenthesis, then we've got an error, so we return null. Finally, if we saw a negation sign, then we pick it up, we scan it. Oh, I should put parentheses there. And then we call Parse Factor to pick up another factor, and then we build a new object. Here we're saying new, and we build a negate object whose argument will point to the factor that we just parsed. And if it's none of those things, then we return null. It was an error. Let's keep going with the function that parses expressions. Before we go any further, let me say that there's a problem with this code, and I'll talk about that in a second. So an expression is t plus e, or t minus e, or t alone. So we start in all three of these cases by picking up a term. So we call parse term. And then we see whether we've got a plus or a minus. If we've got a plus, then we pick that up, and then we pick up the e. Okay, that's calling parse e right here. Then we build an add node using the first term that we parsed, followed by the expression, b, and then we return that node. If we have a negative sign instead, then same thing. We scan the negative sign, parse an expression, and then we build a new subtract node with those two things, and then we return that. And finally, if there's not a plus or a minus following the t, then we simply return the term itself. As I said, the function, as I just presented it, has a problem. It doesn't handle associativity correctly. To see it fail, let's look at this particular example. An expression goes to a term minus an expression. Okay, so the relevant code, we pick up the t by calling parse t. Then we check and see we've got a minus sign, so we call parse e to pick up the expression, and then we build a subtract node with the term a and the expression b. Okay, let's look at this particular input, 7 minus 5 plus 1. And according to our rules of associativity, we do the subtraction first before the addition. So the way this thing will handle this expression is it first calls parse t to pick up the 7, okay, and then it calls itself recursively to pick up another expression. So this call right here picks up the 7, then we see the minus sign, then we call parse e to pick up everything else. And so then it's going to build a subtract node with the 7 and everything else that it picked up. So it's going to return a representation that looks like this tree here. Minus sign at the root, 7 on the left, and then everything else on the right. So assuming that the rest of the expression is parsed, and that's 5 plus 1, so we have 5 plus 1 here, and our final result will be this. But this tree has this meaning. It means take 7 and subtract the result of adding 5 plus 1, and that is not the correct interpretation of our input. So now let's talk about how to fix this. We could always take our original rule and reverse the t and the e. So here we are producing a new rule with e plus t and e minus t. And that is a correct grammar, and the language it describes is the same. And in fact, it models the associativity correctly. However, our recursive descent algorithm will not work with this particular grammar. So let's take a look at what happens. Here's our parse e function and we've now rewritten it using the second rule. So the first thing we do is we parse an e. Okay, here we call parse e, and then we check the next token, and if, for example, it is a plus, then we parse a t. So we scan the plus and we call parse t, and then we build a new add function using the result of parse e and the result of parse t, a and b. However, this is infinite recursion, right? Parse e, the first thing it does is call parse e itself without scanning any tokens. So this is infinite recursion. Nothing will ever get scanned, and this is a problem. In general, the problem happens when we have rules like this in our grammar. A goes to something else, and the right-hand side starts with the very same non-terminal. See, we have that right here. E goes to E plus T. Okay? We can also have more complex situations. For example, A goes to a rule that starts with B. B goes to something that starts with C, and there's a rule for C that starts with A. So with grammars like this, we cannot use recursive descent parsing. Fortunately, there's a nice simple solution. What we're going to do is rewrite this rule as E goes to T, followed by 0 or more occurrences of plus T, minus T, plus T, minus T, and so on. Here's what the code now looks like. For the parse E function, we first call parse T to pick up the first term, and then we have a loop. So this is a infinite loop with a breaking by returning. We look at the next token. If it's a plus, then we scan it, and then we parse another T, and we build an add node, and we keep going. If it's a minus, we do a similar thing. If there's no plus or no minus, then finally we return A. So we're building up A all the while. I've left out the error checking code here, but you could figure that out. It's pretty straightforward. We just check for null. So let's see how this thing works on a particular example. We're parsing our 7 minus 5 plus 1. So we start by calling parse t, and we pick up the 7. Okay, so that's what we get here. At this point, we've parsed the 7, and we've got A pointing to a 7. And we go into our loop here, and we see that there is a minus sign. So what we're going to do is scan the minus sign. We're going to call parse t, and then we're going to create a new node, a subtract node, and we'll call it A. And we're going to use as the left pointer the pointer to the previous A, that is the pointer to the 7 node, and B, the new term that we just picked up, which is 5. And that will become our new A. Okay? And then we repeat the loop. And what happens? We see that the next symbol is a plus sign. So we scan the plus sign and call parse t. And here we pick up the 1. And we create a new add node using the old previous tree, A, which is this tree right here, and the new one that we just picked up, the integer 1. So here we build our new node. Our left pointer goes to the previous version of A, and our right pointer goes to the integer 1. So this is a tree. It's not written very much like a tree, so if I reorganize it, you can see that the top node is an add, left goes to a subtract, and then it's subtract 7 minus 5, and the other operand to the addition is 1. So it is this interpretation that this code will build up. The rule for t is similar. We have to modify it in a similar way because it has the same infinite recursion problem as it's written right now. But I think you can do that. I taught compiler design and theory of computation for several years, and the whole subject of languages and grammars and parsing algorithms is really quite fascinating. There's really a lot to it. Basically, we can break down languages and parsing into several different categories. We have LL languages, LL parsers, LR, and everything else. We've been talking about something called LL1. Our grammar is LL1. That stands for, the 1 is for one token look ahead, so we can basically see where we're going just by looking at the next token. It's great because we can create top-down recursive descent parsers. That's a very fast and simple algorithm with good error reporting. And these languages, LL1 languages, are very easy for humans to parse. And another thing that's important is we have good error reporting and good error recovery. The user often will have incorrect input, and that can really confuse a parser. We want to avoid printing out 1,000 different messages from one single error. We want to print out a nice concise error that tells the user what they did wrong. There is a class of languages called LLK, and LL1 is the simplest version of that. And as I said, the grammar that I presented here is LL1. We've also got more complex grammars in languages called LR, LRK in general. There's some variations, SLR and LALR. I'm not going to go into what all these stand for, but these are necessary for more complex programming languages like C and C++ and Java. The algorithms for parsing are more complicated. In fact, they're really quite complicated. I've taught them for many years, and it's really hard for the students to understand. Hard for me to understand at first, in fact. These languages are also harder for humans to parse, and I think that's really very relevant. I don't want a complicated language particularly. Life is complicated enough without the unnecessary complexity of languages. These languages also are more difficult to create parsers that produce good error messages and recover appropriately from errors. So that's really a practical issue. Beyond the LR and LL grammars, we have ambiguous grammars and ambiguous languages, and it gets even more interesting after that and gradually goes into the theory of computation, but that's for another video. One thing you may have heard about is parser tools, also called parser generators. The idea with one of these tools is that the input is a grammar. Okay, so you're putting a grammar into the tool, and the output is a parser, or more precisely, code for a parser, or something that you can embed in your own program. And the idea is that these tools are supposed to make writing a compiler easier. I do want to say that parsing is definitely not the hard part of writing a compiler. Having written several compilers, I've learned that the parsing is really the easiest part. In fact, my opinion is that I prefer to avoid parser tools altogether. The tool can break. Software rot is real. Things that used to work suddenly stop working because of upgrades and other software that they depend on, and it's complex. It's a huge problem because what if the tool breaks? Then what are you supposed to do? You can't necessarily fix the tool. I generally prefer to use my own code. I like to program. What can I say? I also believe very strongly that LL languages, like I've just demonstrated, are really superior to LR and more complex languages for defining programming languages and other sorts of computer input. LL languages are easier for humans to learn and to use. Humans have to parse the input. Humans read programs and they have to be able to do the parsing. And these LR grammars can be difficult in certain situations. So it's hard to understand what it is you're reading. So that's an important aspect. Simplicity is always good. Simpler parsing is also good. These LL languages are easier to parse, they're fast, and we can have better error reporting and error recovery. And I feel that LR grammars and LR parsers are basically just unnecessary complexity. Oh, that's my opinion. Anyway, thanks for watching my short tutorial.